Okay, so here we have a PB7200. This is one of our revision 2 instruments, one of the early instruments. We have the control electronics and the lasers and the locking amplifier and battery are all contained in this control unit. The control unit is connected by an electronic cable and a fiber optic cable to a source photomixer. Terahertz radiation is generated through heterodyne mixing. We have an off-axis parabolic mirror that sends the terahertz radiation through the sample area, where it's another parabolic and then is focused onto a receiver photomixer, where homodyne detection occurs. So let me take the lid off of this unit and show you what's going on inside here. So here's with the lid off, and what we have here, we have 2 lasers, this one here and one here. We have a fiber optic splitter, 2x2 fiber optic splitter. The output from both lasers is fed into it. It's combined, and then half of the power of the 2 lasers goes to the source photomixer and the other half goes to the detector photomixer. Generally we don't have connectors in here, it's all spliced together. Here's the motherboard. Here's a space for the battery pack. The DSP can't be seen under here. Completely contained. It'll run off either the battery or off a wall wart, and it's USB control. So I have started up the software for the PB7200. It's fairly straightforward. Start frequency, end frequency, step size. This is for scanning. We also have a tab here on the left for dwell if you want to just go sit at 400 gigahertz. You can start it at 400 gigahertz and it'll take a little bit of time. It shows you what the actual frequency is as it stabilizes. Okay. What we're really interested in is looking at the fringe from this interferometer. So to do that, we're going to move over to the scan, and we're going to scan. I'm going to choose 450 to 650 gigahertz, and I hope you can see this in the video. And then I've chosen a step size of 1 gigahertz, but you can go down to 100 megahertz if you want. Our time constant is going to be 100 milliseconds, so that's for the locking amplifier integration time. And you can average scans with this software, but in order just to make the point, we're just going to be doing what we call a zero scan, which is a scan up. A single scan would be a scan up and back. And here we have a function called weighted smooth, which I'll discuss after we take the data. So let's go ahead and take this data. And in this case, I'm going to kill 2 birds with 1 stone. I am going to take this as the background data. So this is what you would be subtracting from your sample data. Okay, and here we go. So here's the raw data. This is a fringe pattern. The terahertz local oscillator on the detector is coming into and out of phase with the terahertz radiation moving through our sample space. And sometimes it's in phase and constructively adds, and sometimes it's out of phase and destructively adds. This is the voltage, which we're squaring to get the power. This is the voltage on the receive photomixer. Right? And there we go. That was quick and easy. All right, so if you are going to do solid samples, then this, what researchers typically do is let me see, smooth power, you can just smooth away those fringes, make them go away. Right? We are going to take a look at a sample of lactose. So let me put that in. Okay, and now we're going to take the same data Again, here's this raw fringe pattern from the interferometer, and here's when you smooth it away. I've put in the lactose sample. Let's take some data. Now the lactose should give us a very broad signature at about 530 gigahertz. There should also be some loss due to scattering because it's an awfully thick lactose sample. So we see absorption, and then we see the feature, spectroscopic feature there of lactose. Now, if I start turning off the smoothing, let's look at it when it's an actual fringe pattern. So the fringes don't line up completely. Like over here, here's a fringe peak and a fringe null. If you were to try and do background subtraction without doing the smoothing first, you would see a mess, quite frankly. Whereas if you add the smoothing, get rid of the fringes, you'll do background subtraction, and which is this normalized average power. You get this beautiful line at 531 gigahertz, right where you're supposed to. Let's go back to smooth power. Let's take a look at that if we turn off the smoothing. Go back to normalized. Not quite so pretty. This isn't on the log scale like the others. Let's turn off the smoothing altogether. Now the smoothing does have the effect of increasing or decreasing the resolution. All right. Okay, so what I've done now is I have adjusted the heads through trial and error to a point where the interferometer is almost completely balanced. And so we're going to take a look from 200 gigahertz to 700. And unlike the previous scan, there shouldn't be that many fringes. Hit start, and I am going to save this one as a background again. Clear the sample. Okay, there is no sample. Now what you would like to do, you would think, is adjust the heads so that the fringes are far apart, and you can do some spectroscopy in the gaps between those fringes. But there are some problems with that. First of all, it gets very noisy because slight changes in the temperature, in the wind currents, vibrations will cause a slight shift in the phase of the source terahertz radiation to the detector or the local oscillator radiation, and that will present itself as intensity noise. Well, here's the raw power. As you can see, there are no fringes so far. I've adjusted this pretty well. Oh, there's our first fringe. And again, extremely noisy. Another fringe. Okay. Now what we're going to do is we are going to install a sample. Let's take a very simple sample. What I have here is a piece of mylar, about 10 microns thick, taped to a washer. It just makes it easier to hold it in the beam there. And we're going to look what happens. So the idea would be, this is our background, We'd like to subtract it from our sample, which is going to be the mylar, and be left with a nice line like we had with the lactose. And while that's scanning, I'll talk a little bit about what you see here. As we mentioned, one of the things you'd like to do is to adjust the system, something like this, so that your fringes are out of the way and you can look at the, say, gas transition that you'd like to see without the interference of a fringe. The issue, however, is that fringes will pop up wherever you have a strong absorption. For instance, here is 556.9 gigahertz right in here, and look, magically we have a fringe there. As soon as you put an absorber in the sample cell, the index of refraction around that absorption changes dramatically, and you almost always get a fringe to appear. Well, that's another issue when you're trying to do fringe-free spectroscopy on an interferometer. But let's just see what happens here with this piece of mylar that we've inserted. Okay, there's a shift here. It doesn't seem that large. And there's some reflection going on, so the power is lower. If we go to the second fringe, do subtraction. When you do the subtraction, you see that the fringes had shifted slightly. Okay, so I have put in a lactose sample, and I'm kind of curious what's going to happen. As you recall, in the previous part of the video, we had put the fringes close together and smoothed them away, and we got a beautiful absorption feature from the lactose, and we were able to subtract the background in that case. So let's see what happens with the fringes spaced far apart and the lactose really changing the balance of the interferometer. Go to raw power here, and that's a fringe. And there we have another fringe. And there's our lactose absorption. And what I want you to notice is here is a fringe right next to lactose. It comes back to what I'm saying. Anytime you have a strong absorption, you're going to cause fringes near that absorption. And this fringe has disappeared completely. There we go. Now let's go look at our, I guess on a log scale it doesn't look, a linear scale doesn't look too bad. But if you're looking for small features, you might attribute those to being absorptions when they're actually issues with the fringe.